Hello, everyone. Welcome to this virtual tour to Paranal Observatory from ESO, the European Southern Observatories. My name is Hernan Julio. I'm a journalist specialized in astronomy. And together with my friend here, our producer today, we want to welcome him. Hi, Hector. How are you?
Hi, Hernan. I'm happy to be here and be part of another tour of Paranal Observatory. So, allow me to introduce myself to the audience. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany, and I've been part of the team or the team of guides for Paranal Observatory since 2019. But since the last couple of years, I have only been virtual, assisting with these tours because I'm in Germany, not in Chile. And for my work, I mostly work on the circumgalactic medium, that is the environment that surrounds galaxies. And as Hernan says, I will be the producer today, and that means that I will be looking at your questions, your comments, and try to come with the right answers for them.
Yes, thank you, Hector. Well, as you see, Hector is in Germany and I'm in La Silla Observatory here in Chile. So, thanks to this technology, we can be with all of you. And we thank you, especially Radna Ayu, that is talking to us in the chat. Also, Scotty Orange. Hello from Virginia. Scotty, nice to see you. We were in Virginia a couple of months, 1 month ago. I was in Virginia, so nice, nice place, nice state. Well, please keep send your questions, your comments in the chat. We would love to answer all the questions that we can, and of course, we have Hector here, who is a PhD student. So all those difficult questions, he's ready to answer to you. So, but let's start with this tour, with this virtual tour. First of all, I want to introduce you ESO. The ESO is the European Southern Observatories. Okay, the European Southern Observatory is an international organization. Okay, this international organization started in the 60s, 1962, actually, with only 5 countries. Later on, many other countries start to join this international organization. Okay, in your screen, you can see these countries that today are part of ESO. Denmark, the Netherlands, United Kingdom, Ireland, Belgium, France, Portugal, Spain, Sweden, Finland, Germany, Poland, Czech Republic, Austria, Switzerland, and Italy. And we also have a strategic partner, which is Australia. As you see now, ESO is not just an European organization, it's a global organization. And of course, Chile. Chile is the host country. Um, the main observatories of ESO are in Chile because our conditions, you will see through this virtual tour, the excellent astronomical conditions that are in Chile. Actually, this organization, ESO, is celebrating the 60th anniversary in Chile. The organization started in Chile in 1963. We're in 2023, so we're celebrating our 60th anniversary. The first observatory, actually, in Chile was inaugurated in 1969. In the today's ESO has 3 main observatories in Chile, which is you can see it in your screen now. Yes, in the center, a little to the right, it says La Silla Observatory with ESO 3.6-meter telescope, and the NTT, the New Technology Telescope, was inaugurated in 1969. Okay, so it's a classical observatory. Actually, I'm right now I'm in La Silla Observatory, and later in the 90s, ESO start to build the VLT and the VLTI. The observatory and the telescope that you are going to get to know today. The VLT are 4 8.2-meter telescopes. Okay, in the same mountain, well, close to the same mountain in Paranal, we have the VST and Vista, which are two main telescope. These are survey telescope, which are in the same observatory that the VLT and the VLTI. And very close to us is the CTA South. Okay, the CTA is about 100 special telescope. They're going to be ready in the next decade to capture all the gamma ray burst, okay, all that kind of telescope. And of course, we have our main project for this century is the ELT, the extremely large telescope, which is only at 20 kilometers from Paranal, northern Chile. As you see in the map, Paranal is about 1,000 kilometers north from Santiago de Chile, which is the capital of the country. Okay, if you come to Chile, actually, we have tours every Saturdays in Paranal to a tour that you can come and walk around the telescope, go inside the telescope. The same thing that you're going to do virtually here. We will be waiting for you every Saturday at 10 a.m. in the morning and 2 p.m. in the afternoon. Okay, and Paranal, as I told you, if you take a plane, it would take you 2 hours and a half, about 2 hours and a half to fly from Santiago de Chile to Antofagasta city. And Paranal is about 1 hour and 20 minutes, 1 hour and a half driving from Antofagasta to the south. So let's go to Paranal. Let's go to the telescope to get right away to know to them. We are flying right now over the desert, the Atacama Desert. The Atacama Desert is the driest desert in the world. That's why we are in this place. Okay, why is so important that it's a dry desert? Is because the atmospheres around us, it has almost no water. Okay, no water vapor. Very important because the light that is coming from the star that are thousand billions years ago away, light away. The light have to go through the atmosphere. So if the atmosphere has water, for example, our image are, are going to be not good as we would like to. That's why we're here in the driest desert in the world. Here we are very close now to the mountain called Paranal. The observatory take the name of the mountain. That's because we talking about the Paranal Observatory, and the telescope is the VLT, the Very Large Telescope, and VLTI, the Very Large Telescope Interferometry. We will going to have a video showing us the platform of the telescope. We're going to get close now to the platform. Here we are. This is the most advanced time machine, astronomical time machine on Earth right now. You can see four big telescopes. Those four big telescopes, they are 8.2 meter each. That means that inside of this telescope, each one of them has a mirror, main mirror of 8.2 meter in diameter. And as you can see also, we have this small telescope that looks like robot. We call it AT or auxiliary telescope. The 4S small telescope, each one of them has a 1.8 mirror in diameter. Okay, all of them all together they work in a mode that we call interferometry mode. But for to talk about this interferometry mode, I'd rather to go down to the telescope. We go to the platform. We have this 360 degrees tour, and we are going to show you a little bit first where we are. We are, as I told you, in the heart of the Atacama Desert. Okay. Well, while we're taking this gorgeous view of the desert and the observatory, I want to say hi to Sway Graven from Amsterdam, also Mr. Stogowski from Glasgow, Scotland, and Bon Dia is telling us Helio Santos, Atacama, Amazones. So please, if you have a question, you can write it in our chat or say hi and tell us where you are looking us from where you are in the world. Well, here is we're in the platform, Amazones, excuse me, the Paranal Mountain was cut in 28 meters. We cut the top of the mountain to make this platform flat in order to build the telescopes. Okay, you're looking now at the four big ones and the four small ones. Well, this telescope work in a classical mode. That means that you point each of each of the telescope to a different star. But the important part of this, the most advanced part of this machine is that the four telescope and the four small telescope and the four small, a big telescope can work together. That means that you can point all the telescope at the same time um, at the same star, and you will have the VLTI, the interferometric VLT interferometric, very large telescope interferometric. That means that we are going to get an image very sharp with a lot of details. Okay, very important for astronomy. Okay, I think there is a video that we can show to them how this works. Here we have the platform, we have the four big telescope, and now we are going to have if you point the four big one together to one object or one star, for example, you will make a virtual mirror of 130 meters. But if you use the big ones and the four small one, you want to have a virtual mirror of 200 meters. How we do that? Well, we capture the light from each telescope and we send that beam of light underneath to the building that is in the center. In the center, which is the interferometric lab, all the light from the all mirrors get together at the same time, and we build this virtual telescope, making of this machine the most advanced telescope on Earth right now. Mm. I would like to also say hello to some other people that is with us. Moses Gira from Uganda, also Tom Okay, and Mr. Stogovsky is telling us that he applied for a job with ESO a few days ago as a telescope operator in Paranal. Very interesting to find out more about the observatory. I might be working with you soon. Oh, that will be great. Say hi to us when you are with us, okay? Good luck with that application. Also, we have a blue dot with us, Muhammad Sabit Khan from Pakistan. Astro Runaway, Tegucigalpa, Honduras. Bienvenida. And Svin Varillas also is with us. Well, I would like that Hector maybe explain a little bit in a little more detail what interferometry is. If I don't know if there is any other questions. Anyways.
Okay, so what I can comment on interferometry. So one of the things that is very interesting here is that the auxiliary telescopes, they are mounted on rails that you can see here on the screen. And you see these octagonal doors. There are about 30 of them in this platform. And we can put the auxiliary telescope in any of those 30 positions. Now, why is that important? Because when we're doing interferometry, we are we care about what we call the baseline, and that is the separation between the telescopes. So when we change the position of this auxiliary telescope, we change the baselines, and that means that we change a bit the resolution. And when we say that we improve the resolution using interferometry, what we mean is that if there are two stars, for example, that are very close in the sky, without interferometry, they might look as a single big object. But with better resolution, when we do the interferometry, we might be able to differentiate that they're two separate objects. So you can see things better that way. But what we cannot do is increase the amount of light that we can collect. This is like putting a bucket in the rain. The larger your bucket, the more rain you collect. The larger your telescope, more light you can collect. And therefore you can see objects that are either intrinsically fainter or that are farther away. So that's why we are not only doing interferometry, but we're also building very big telescope like the ELT, because we want to see things that are fainter as well. And
Great. Thank you, Hector. Well, we have here a question from Blue Dot. Say hello from France. Can you tell us when is planned the first flight of the ELT and explain how process this huge amount of astronomical data? Thank you. Well, first about the ELT, we're thinking that the ELT will be the first light up around 2029. Okay, but this project sometime because of pandemic situation or whatever around the world can be delayed a little bit. And about how is processed this huge amount of astronomical data, I think Hector is the best guy to answer that question.
Okay, this is actually one of the big problems or big topics in astronomy in the last 10 years or so. Astronomy entered the era of big data. So astronomers, they are now usually not working with single galaxies or single stars, but with thousands or hundreds of thousands of them. And how to deal with this big amount of data? Well, we are using things like machine learning. That's something that is improving every day. But also things like citizen science projects, like the Galaxy Zoo, for example, in which images of galaxies are uploaded to a web page or to an app, and everybody can create an account and help the scientists to classify these galaxies. So that's actually something very fun if you have like 5 spare minutes of your day. You can join to that kind of projects. But yeah, it's a challenge, and astronomers are increasingly learning more about computation and how to do statistics and how to do this in a better way. So, so yeah, we're
All
working towards
right.
that.
Thank you, Hector. Well, we have one more question here. This says, Esvin Varillas, how much does the tour cost? Does the tour include night observation through the telescope? Well, the cost of the tours, the tour that we make every Saturday at 10 o'clock in the morning and at 2 p.m. in the afternoon are free. You just have to arrive. Well, first you have to book in our webpage. In our webpage, you will find a link which is very easy to book in your tour for any Saturday of the year, and that is free. Is only in the day. Okay, people that is not astronomers that are working or engineers that are working or staff, astronomer staff or whoever is working in the observatory have to leave before 5 p.m. Okay, so visitors have to leave before 5 p.m. in the afternoon because at night, of course, light pollution is a problem. We keep all the lights down, so it's very dangerous to drive around or to walk around. So far, the tours are all in the day, but they are free every Saturday again at 10 p.m. and 2 p.m. So if you're planning to come to Chile, please visit our webpage, ESO.org, ESO.org from organization. All right, so let's continue with this. Let's say hello to Virgilius Staselis from Lithuania. Also Miguel Villalba from Argentina. Well, hi, hello, Miguel. And Esvin, Esvin Varillas, he says from Guatemala. Um, well, we have a lot of, thank you for your comment, thank you for your questions. We will be answering your question through the tour, and we have to continue. We have to go now inside of one of the telescope. Okay, so we want to show. Before that, Hector, the telescope, the four big telescopes are the same inside and outside. They have Mapudungun names. Mapudungun is the language of the inhabitant from the southern Chile, the Mapuches. And the first one is Antu, the second one is Cuyen, the third one is Melipal, and the fourth one is Jepun, which means sun, moon, Southern Cross, and Venus. We're going to inside of Melipal, okay, which is Southern Cross. Here we are, okay? As you can see, let's have a view, a panoramic view of the telescope. With the inside of the telescope is a huge telescope. I already told you that we're talking about an 8 meter um, mirror diameter. I think we can go closer to the mirror. There we go. The mirror is the heart of the telescope. The mirror, as I told you, and that you can see, is 8.2 meter in diameter. It's about 17, 18 centimeters of thick, and it has a surface of aluminum. It's like a skin of aluminum over the mirror. Okay, that aluminum is the one who reflect the surface. Aluminum surface reflect the light. Okay, and the mirror always is curved. Okay, why is that? Because in the night we have to open a window. Okay, of the enclosure of the dome. You can say that the white part that you can see in the back part is the window. We open up to the half of the roof. Okay, it's like a window, and then we pointed the telescope to the star. So the light will go inside of the telescope and will reach the main mirror, then will be reflected to the secondary mirror. Up there is a tube, black tube that you can see in the upper part of the mirror of the telescope. There we go, that's the second mirror. And then the light goes down again in a dim of light back and go through the mirror because the mirror has a hole in the middle. Um, there is a tube actually and go down to the instrument. Okay, there is an instrument in the hanging from the back from the down part of the mirror of the telescope, and also we have an instrument to the right. Here we have a video which is showing us how the lights go inside of the telescope. First, the light will reach the main mirror, as I told you, and then the light will go to the secondary mirror and back again, and we go to the sides. That red box and also that blue box and the green box in the bottom of the telescope are the instrument. Okay, the instrument replaced today in the 21st century is replacing the human eye. Okay, the light will be gathered from this instrument with the CCD, and the information will go to the computer room. Well, here we're back inside of the telescope and we can see the instrument. Maybe we can show one of the instruments. There we have one of the big instrument, the one, remember there is one instrument in each side, and then we have another instrument in the back. Maybe we can go down to look from the bottom part of the telescope. Here we are. This is the instrument, in this case is Symphony. This instrument is in the bottom part of the telescope. And one very important thing that I have to tell you also is that what we are looking at is what we call the M1 or mirror one, main mirror, cell. Underneath the mirror, we have what we call actuators. Okay, these actuators are these boxes that you can see there that are pushing up and down the mirror in order to keep the surface always perfect. Okay, remember that we're talking about 8.2 meter in diameter, and it's very thin. That means that the mirror in the night could lose the curve of the surface. We're talking about nanomillimeters. So we have a computer who detect when the mirror has this error, okay, this mistake in the surface, and correct it in real time. That means that while the astronomer is observing the object, the mirror is being corrected all the time. Okay, that is called active optic. Active optics is one of the most modern technology used in astronomy in all the new technology telescope. Okay, and we are in the bottom part now of the telescope. Okay, also maybe we can go back up to the here we are. See, we can see, and then we have, as you could see, one instrument is each in each side and one in the bottom. Also, these instruments are different instruments. Usually, they are visible, infrared, and ultraviolet. So the astronomer will be able to change instrument as he wish or she wish. Okay, let's see if there is any question. I think there is one from Virgilius Stacelis. VLT operates in visible light range or only or also covers infrared and ultraviolet spectrum range. Hector, please.
That really depends on which instrument you're using. So, for instance, the instrument that I have used the most for my PhD is called Muse. is in the UT4 telescope, and MUSE is goes from not really the ultraviolet, covers a bit of it, but not very much, and to a bit of the infrared. So it's mostly visual. And now the institute where I'm working is developing the successor of this instrument that is called Blue Muse, that is going to cover more towards the ultraviolet, because the current Muse covers more towards the infrared than towards the ultraviolet. But
All
depending
right.
on this instrument, you can have visual, ultraviolet. So the thing that is going to limit you what you can observe is going to be, well, the atmosphere mainly. There are things that just simply cannot be observed from inside the Earth, and you need to put satellites in space. But for the rest of the wavelengths, you can pretty much observe anything. Now, keep in mind, this is a facility that works with mirrors, not with radio waves. So that is also going to limit what we can observe here. So we're not
All
working with
right.
antennas.
Mm-hmm. Well, thank you, Hector. Thank you also, Virgili, who's for his questions. And we also have another question. Say, how do you find working in such a remote location, and what is the challenge of the desert condition? Well, yes, it's a challenge. But it's a nice challenge. I like to work. I'm a desert boy, so I like the desert more. I don't like too much rain, so it's very nice for me to work in this kind of environment. Of course, for example, in Paranal, it's in the heart of the Atacama Desert. We need to bring the water from the near city, which is Antofagasta, and it's a challenge. But it's very nice. Of course, also we work here. The people work in shift. People have shift, 7 day shift, 10 day shift, weekend shift, etc. So for us, it's a challenge. And also, anyways, the observatory has all the conditions for to have a nice stay while we're working the telescope in the observatory. Thank you. Thank you. Well, we have to continue, I think, because, I want to say hello to Snowy, also is with us. Uh, Maria Marie is a very interesting guide to this handsome place. Can I ask which language? This is a question for you. Can I ask which language program used the symphony to control the actuators? You know that, Hector?
Okay, so to clarify a few things, so symphony is an instrument that is a detector, like a camera, if you wish. It's not related to the actuators. The actuators are independent of the instrument. So it's not just the actuators are there for all of the different instruments, not just for symphony. Now, which kind of programming language does he use? Honestly, I don't really know. Like in
Yeah.
astronomy, right now, Python is the most used language, but you can still see people working on C, and you can see people working in Fortran for some reason. There's a wide variety. And like 10 years ago, the most common was IDL because it's very good with images. But that is for the astronomer processing of the images part. For the movement of the instrument, that could be a whole other different language. So I cannot really answer you that right now. Sorry.
Well, yeah, more the general, Python is the most general language that we're using now in the observatories in general. Anyways, we have to say hello to Tom. Okay. Also, he say, how do you recode the aluminum surface? Well, we have to take out the mirror from where you see it. We have a aluminum chamber, special, away from the telescope. We have to take out the all aluminum with a special chemicals. It's a, of course, automatic machines, and then we re-illuminate the mirror, and then we take back the mirror in its place. Okay, it's about a 10 days operation. Is the most, I would say, the most dangerous operation that we have in the observatory. And of course, we don't do it every day. We do it every 2 years or 18 months, around that. How deep or how far back in the time can you look using VLT? Well, the VLT is an amazing machine, and we can reach most of the visible universe. That means that we can reach even those light that are the first light of the universe, the first stars or the first galaxies in the universe. So we're talking about 12 billion years ago. Okay.
Yeah.
Thank you very much for the question, but we have to continue with the with the tour. And now we want to show, you can see people working inside of the telescope, but they are working in the day. This is the day picture. In the night, the telescope is totally dark. So in the night, the astronomer work in the control room. So let's go to the control room to show you from where the astronomer works. You have to walk out from the telescope, and that's the building where is the control room. We're going now to the control room. This is the building. There's a section of the building where the astronomer works. And here we are. Okay, it's a computer room. So that means that there is computers. I think the best person to explain you what's going on here in the night is Hector. Okay.
Yeah. Okay, so you see here a lot of computers, a lot of screen, a lot of people. And let's move here. Now, this part over here is just for a single of the Big Four telescope. So why do we have so many screens and things? Well, you have to remember that we have three different instruments in each telescope, so they may have a dedicated computer for each one of them. You may also have a dedicated computer just to move and control the telescope. And you also want to have a screen with weather information. That is very important. If the humidity is too high, you need to close the telescope. If the wind speed is too high, there is the risk of small pebble or rock to be lifted and crashing into the mirrors, which could be very bad. So you also need to close in that case. But usually the weather in Paranal is very good. We have over 300 nights per year that we can observe without any problems. Now, at night here, there will be only two people working. Even though we see many chairs here, there will usually be two people. So there will be one telescope operator and one astronomer. So we can think this as a pilot and a co-pilot in a plane, or a pilot and a co-pilot in a rally car. So the telescope operator, he's the pilot. He's controlling the telescope. These are very advanced telescope, so the astronomers they don't handle them. There is a specific job that is just to control the telescope and its instrument. It's a specialized job. What the astronomer is going to do is he's going to supervise the observations and take care of the scientific part. He's going to be like the co-pilot, telling the route, telling where to turn and what to do next. What what do you have to do to be able to observe here? Well, any astronomer from any country in the world can observe here, but they need to apply for it. There are two times per year when you can apply with your scientific project, and a committee will check all the projects and decide which one is best based on the scientific merit. And these application times, they are very specific. You have to say which object you want to observe, with which telescope, with which instrument, how many observation time do you want, how far away the moon needs to be for the observation to be usable, whether this object has been observed with other instruments before, what kind of science you want to do, etc., etc. And Paranal is one of the most competitive places in astronomy to get observation time. It's oversubscribed by a factor of 7 or 8, I think. So it's very hard to get time here. And if you get time, then you can choose between the service mode and the visitor mode. So in the visitor mode, you will travel here, you will sit on the chair, and you will be supervising the observations. In the service mode, you will not travel here. You will give the instruction to an astronomer of the observatory staff, and they will supervise the observations for you. About 70% of the observations are in the service mode and 30% or so in the visitor mode. And then you have your observations. They are going to be private for you for about 1 year. You have that time to do your research, and after that time, everything is going to be made public. There is a website when any astronomer or any person that creates an account can go and can request data that has been already made public. Now, astronomy is a very collaborative science. So what you usually will do, you will email the person that submitted that observation project, and you will tell them, I want to do this type of science with your data, and is it cool? Do you like it or not? Maybe invite them to work in the project as well, and people usually agree. So that's more or less what you have to do for observing and getting your images.
All right. There is two nice question for you, Hector. I think this is are the longest exposure that ESO has done using the VLT, and will it be different with the ELT? Thanks.
Okay, so I'm currently working with a very deep field that is called the Muse Extreme Deep Field, and in total is 150 hours of observation. That is ridiculously long, and it costs a lot of money if you think about it. But now, it wasn't continuous 150 hours. It was shorter observations that were taking up the same part of the sky, and then we combined all the observations to make this large data set. And in this particular case, you were rotating the telescope with every observation so that the light doesn't always fall in the same part of the detector. So yeah, you can go very deep if you have a nice project.
Yeah. And another question for you says, what is your favorite telescope from Paranal and Instruments?
Well, for me, it's Muse. So the
Of
Muse
course.
instrument is my favorite because I use it for my master thesis and I'm using it for my PhD work. And that is in the UT4 telescope, Japan. Uh, Hernan, what is your favorite of these ones?
Oh, I like UT4 because the laser, uh, the, the laser. But I think the laser is very photogenic at night.
Yeah, that is
So
something that we haven't really covered before. So maybe we should mention that there is a
yeah,
system called adaptive optics that is used to contrast the effect of the atmospheres in the light, and it uses lasers. And there are some very nice pictures of the lasers. And only the UT4 telescope has the lasers. At first, it was only one laser. Now it has four lasers for the system.
yeah, it's very nice. I recommend you to go to our webpage eso.org or .ca also. There you go. There we have a picture with the laser, and
Yeah.
you will be able to see all this picture in our webpage. We have a thousand, we have a tons of pictures and any resolution and also videos. So go there and take a look at it. Well, we have to continue, but I think that one important part is let to know to our friends around the world what main discovery has ESO made with the telescope in Chile. I think we have a video ready for that.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
All right. Well, that was the 10 top discoveries from ESO, but now we want to show you something that we cannot do at daytime when you come to have this presential virtual tours. When you come Saturdays, as I told you, it's in the day, every Saturday at 10 o'clock in the morning and 2 p.m. in the afternoon. But you won't be able to see the night. You cannot be in the night in the observatory. But thanks to this technology, now we are going to show you how Paranal looks like at night. There we go. Okay, this is the gorgeous sky over Paranal. Actually, we can see some of the northern constellation. Here we have the Orion constellation, what we call in this the Orion belt there. Well, that's the Orion constellation, the Orion belt. We also have the Orion sword and the Orion nebula. Okay, that little nebula that is there. This picture is taken with a camera, not with the telescope. Just and you can see how great is the picture. Okay, a little down we have also Taurus constellations, and there we are. Is Taurus constellation, and even a little down is, of course, the Pleiades, okay, or Subaru in Japanese, okay. These are the constellation and the object that you can see from also from the northern sky. But I would like to show you the southern sky. For those that are in the northern hemisphere, are not able to see this uh, wonderful sky, the southern sky. The first thing that we can notice are the Magallanes clouds. Okay, those two dots to the right are the Magallanes clouds. They're called Magallanes cloud, but they're not clouds. Okay, they're galaxies. They're the two closest galaxies to our galaxy. Actually, these two galaxies are satellite galaxy to us. They're going around to the Milky Way, our own galaxy. They're called Magallanes because was the first navigator who looked to the sky when he did cross the Ecuador and he was in the southern ocean, southern seas. He looked to the sky and he could see this Magallanes cloud, this object. Actually, he used this object to find out the south. Remember that in the southern sky, we don't have the north polar star, which is in the northern sky. Okay, so he didn't know how to find his way to the south, and he used these two Magallanes cloud, making a triangle. Okay, we make a triangle with these two Magallanes cloud, and that angle where now the mouse is pointing is the southern celestial pole. Around that point is all the stars going around, okay? And if you find the point, you can find the south. You just put a line down to the geographical point, and that is the south, okay? If you're in Paranal, for example, if you walk that way, you will go down to Santiago de Chile, which is south from Paranal. At your left, we also have of course, the another constellation, a typical constellation from the south, which is the Southern Cross. Okay, you can see the cross there. Okay, and if you take the longest stick, and you add it three and a half time, you will have also the same southern celestial pole. Okay, so you have two ways to find your south, the south in the southern hemisphere, with the Magallanes Cloud or with the Southern Cross. Okay, also we can see the Alpha and Beta Centaurus is right there, one of most of the most brilliant um, object in the sky. But that's the so far we were talking about the stars, constellation, in the Western way, okay? But in Chile and of course in all Latin America, previous that Spanish came to America, we have also great astronomers, okay? In our country here, we have the Incas, the Atacameños, Mapuches, uh, and many other people from Chile, and they were excellent astronomers also, but they because the sky was so clear, okay, they didn't saw the light. I mean the stars. They used the dark spot in the Milky Way to create their constellations. And now you can see all these dark spots, which are dark clouds of gas and dust. They're so dense, these clouds of gas and dust are so dense that no light can go through it. So you can see this like a black spot in the sky. And here you're looking at what they used to call the bird, okay? What we, the Western, call the Coolsack. A little down, we are going to be able to see the Llama constellation. Actually, in this picture, we only can see the head of the Llama having the Alpha Centaurus like the eye of the Llama. Okay, all this dark dark object that you see, dark cloud, is the head of the Llama constellation. later on in the night, in this time of the year, this constellation goes up and you can see the whole body of the lava. That's the way how the original people from Chile and from the South America used to look to the sky. As you see, we are looking to the Milky Way, and for them, the Milky Way used to be a river. From all these animals came down to have water. Okay, so we thanks to also to these cultures that were in South America and in America before the Spanish came to give us this legacy, this culture and knowledge to us. Well, actually, we don't have too much time left, so we have to come back to the 21st century. We are here, and we want to show you a little bit. There is some questions um, also about how the life in Paranal Observatory. We want to show you where we live, where we are when we are not working, where we are resting in here in Paranal Observatory. Okay, so we will go down. We are right now in the top of the mountain, but we are going down to the camp, the base camp. This is the base camp where you can see we have the warehouse. We have the place where we re-illuminize the mirror, and of course we have our residencia. Okay, the place where people rest when they're resting from working. Okay, a residence is a building. It's a very important building. Actually, a couple years ago, in this building was filmed one James Bond film, Quantum of Solace. I remember that was the name of the film. It's a nice building. The building itself has won a lot of prizes, architectural prizes, because what you will see right now. We go inside of the building, and you can see we have this garden, very important to see green in the desert. It's the only green that you can see if you're in the observatory for 10, 15 days. It's the only green you will see. Also, we have a pool. Also, it's the only water you will see in the desert. So why it's so important this green and water? Because humidity. Okay, remember that we are in the driest desert in the world. About 5% of humidity. That means that when you go inside of the building, the humidity increase, and it's good for you, for your skin, but also psychological good. Okay, it's not just a luxury. It's just because to see green for human is very important to have a connection with the water also. This is the residencia, and you can see there is a dome, but in the night we close the dome. There is in the center of the dome we have a curtain. We close the dome totally, complete, and we don't let any light to go outside. Remember that we are with light pollution, caution. Actually, in Chile, we have a light pollution law. Those cities that are close to the observatories have to have a special light and a special way to lighting the cities. Okay. Well, we also here have, you are seeing the lobby, the front desk of the residencia, and the left and back part, we have the cuisines and the cafeteria where we have dinner, of course, lunch, etc. It's a building that has 108 rooms, and where the people that work in here they sleep. And of course, on day and night you have to be silent because our people sleeping day and night. Okay. I don't know if we have the last 3 minutes to, let's see, maybe um, the last questions, Hector, that we can have.
Yeah, it seems we have several questions.
Um, uh,
So we have a question about, do satellites cause problems for you? Okay, so satellites, they can interrupt the observations, and the big problem is the constellations of satellites such as Starlink and these communication satellites, because there are swarms of satellites. There are dozens of hundreds of satellites moving to the sky at the same time, and they can be very bright. So there is some issue with those satellites. Uh, let's see. We have a
All right.
question.
Well, we're about this exoplanets. I think we
Yeah.
already talked about it. Yes, especially in La Silla. In La Silla Observatory, we have actually TRAPPIST. They call it TRAPPIST system because the telescope, TRAPPIST telescope, is in La Silla. Okay, which is the first observatory that was built by ESO. Um, and yes, we are observing the exoplanets. And of course, as Hector told you, depend. Each astronomer has special interest in different part of astronomy. It's like doctors; they're specialized in different areas. Okay, same thing with astronomy. Well, I think we have to say goodbye. Anyways, we want to invite you to visit our webpage. This webpage is eso.org or eso.cl. Is in many languages, so you can go and read it in your own language. And we thank you. We thank you for to be with us today, and we want to encourage you to visit us. I think there is also we have tours to La Silla Observatory, a virtual tour to La Silla Observatory, and also virtual tour in Spanish and English. So be aware to be looking in our social media to see when is the next virtual tour to La Silla or Paranal Observatory. Thank you very much. Thank you, Hector.
Thank you, Hernan. And please let your friends or anyone you know that might be interested in this tour let us know that every Saturday there is a virtual tour. So goodbye, and we see you in
Right.
another opportunity.
See you next time. Bye bye.